All right, so this is question number 2 of the worksheet of chapter 18. And it says, essentially you've got this reaction that's occurring where you've got 2 phenols and you react it with some ammonia in the presence of bleach here, and you get endophenyl anion, and this is what you're eventually interested in finding. It tells us that this endophenyl anion has light that absorbs as ROBs at 625 nanometers, so this is a wavelength max that we'll be looking at. And it says, now you've got these 3 different samples, and it walks you through what each of those 3 samples is and puts it in a table here, what the absorbance is of each of those samples. So the ultimate goal is to determine how much of this stuff is in lakes, essentially. And so we have a few different things that I want to cover. So let's first go through and walk through each sample, because I like to draw pictures. So let's start with sample A here. You can tell what's important in a problem or even in procedures when you're doing them, in an experiment, for example, by looking at how many sig figs there are. So see how this has 3 sig figs and this has 1 and this has 1? What that tells you is things with 1 sig fig usually aren't that imperative. It usually means you're adding excess of it. But here, this 10 milliliters, 10.0 milliliters, this has 3 sig figs. This is telling you, hey, this is something we actually had to measure and pay attention to. And the same message should be conveyed to you, that this is something we should be paying attention to. So it takes 10 milliliters, 10.0 of lake water. So I just took a sample out of the lake. They mixed it with about 5 milliliters of phenyl. Again, just 1 sig fig, so that's somewhere between 4 and 6 milliliters, telling you most likely there is an excess there. 2 milliliters of the bleach. And then it tells you it dilutes it to 25 milliliters. So your final volume here is 25.0 milliliters. Okay, so ding, 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 there's something with 3 sig figs. This should be taken a little more seriously. All right, so essentially the important things is you had some 10 milliliters of lake water and you eventually diluted it to 25 milliliters. All right, in sample B, similar situation. You have a beaker here. You, again, have 10.0 milliliters of lake water. You have the 5 milliliters of the phenyl. Look, everything's looking the same. You have the 2 milliliters of the bleach. But then you have 2.5 milliliters, 2.50 milliliters of 5.50 mole per liter solution of this ammonia. All right, so as soon as I see liters and mole per liter, I'm thinking we're gonna need moles at some point. So let's go ahead and calculate that out. We have 0.00250 liters times 5.50 times 10 to the negative 4 mole per liter. If I multiply those together, I get 1.375 times 10 to the negative 6 mole. So that's how many mole of ammonia you added. So this is this guy right here to this one. And then you eventually fill it to 25.0 milliliters. And I'm going to write over here 1.375 times 10 to the negative 6 mole NH3. So now we know everything that went into this one. And then it says C is a blank. There was no lake water in this one. You're not analyzing this one. This is just kind of to see what's in the background of the phenyl, etc. So you added 10.0 milliliters of distilled water, of DI water. It's deionized. You added 5 milliliters of phenyl, same stuff, 2 milliliters of the bleach, and then you simply filled it to 25.0 milliliters with more water. All right, so here we have a sample. Here we have a sample with ammonia, and here we have our blank. Now the sample came out at 0.430 absorbance. The one with the ammonia came out at 0.677 absorbance. And this one is 0.045. So this is kind of like our background. All right, so this one without ammonia still had an absorbance at 0.430. Now, what that tells us is that there's something in there at the 625 nanometer wavelength that's absorbing light. And so chances are that there's some endophenol in there. It just, it might not be everything there, because over here, when we added some ammonia, automatically the absorbance went up. So even though we still had 10 milliliters of lake water, chances are over here, maybe you had some unreacted phenol and you added ammonia to it, and that caused the absorbance to go up. All right, so let's work on the first question. It says, what is the molar absorptivity of the endophenol product? Well, to do that, we have to use some kind of known amount. Well, we know that between this one and this one, nothing was different except for the additional ammonia, right? So here, when we added ammonia, all of a sudden the absorbance went up. Well, we know exactly how much ammonia we added, and we know exactly, therefore, for every 1 mole of ammonia, you would have had 1 mole of product, right? So you're able to actually figure out how many moles of this stuff you have in there based on how many moles of ammonia you added. You also know the difference in the absorbance, which was caused. So as long as we can relate absorbance and concentration together, we can find the molar absorptivity coefficient. So absorbance is, the Beer-Lambert's law is A equals this molar absorptivity coefficient times the path length times C. The absorbance wasn't this 0.430, wasn't the 0.677, it was how much it went up when we added this difference right there. So the only thing we added again was that ammonia. You add a little bit of ammonia, look at what happened to the absorbance. It went up quite a bit. In fact, it went up by a difference of 0.677 minus 0.430. It went up by 0.247 absorbance units. All right, now let's set that equal to the molar absorptivity coefficient, which we've got to find, times the path length of 1.00 centimeters, which it tells us right here, times the concentration. Well, how do we figure out the concentration? Well, again, we know according to this reaction that for every 1 mole of this, we get 1 mole of endophenol. We know how much ammonia we added. We just need to figure out how much endophenol there is. So we took of ammonia in this solution, we had 1.375 times 10 to the negative 6 mole of ammonia. And remember that concentration is just mole per liter. We know there are that many mole in 25 milliliters, or in other words, 0.0250 liters. This gives us a concentration of ammonia, which also has to be the same concentration as this because it's a 1-to-1 stoichiometric reaction. And if you take this divided by this, you get an answer of 0.4000000055 mole per liter. And again, that's equal to the ammonia concentration, which is also equal to the endophenol concentration as it reacts. So now we've got our E, we've got our B. Now we can multiply it by our C, 0.000055 mole per liter. Let me clean this up a little bit. And then you take 0.247, divide it by 1, divide it by that 4 zeros, 55, and you end up with an answer of molar absorptivity equaling 4.49 times 10 to the third. And it should oftentimes be big, particularly it's really big for highly colored situations. Liters per centimeter times mole. Once we have the molar absorptivity coefficient, we can figure out the concentration anywhere at any absorbance, or we can figure out the absorbance at any concentration, because now we just have these two unknowns, and if we know one of them, we can figure out the other. So it's a really big step to get here. All right, so this is the molar absorptivity of that. The next question that's asked is, what is the concentration of ammonia in the lake water? Let's go ahead and do this. So we're looking at the concentration of ammonia in the lake. And we've got to figure that out. Well, how are we going to do that? Well, if we go back over here, remember, we know that this blank right here is 0.045, and this has no ammonia in it at all. Yet this one is 0.430, even though this doesn't have any of the added ammonia. So what that means is we can actually figure out how much ammonia there is based on this one right here, as soon as we subtract out the extra noise that's coming from this guy right here. So let's go ahead and do it. Our absorbance is going to be equal, let's see, I'm gonna do a better job organizing it there. There we go. Our absorbance is going to be equal to what we had here, subtracting out essentially the noise. So this is just pure lake water is the way to think about it, unadulterated lake water. 0.430 minus 0.045, and this will tell us that this is 0.385 absorbance units. Okay, so once we have the absorbance from just the lake, again, when we have A equals EBC, since we already know this, the molar absorptivity coefficient, we can find the concentration at any given place. So let's go ahead and just plug and chug. 0.385 equals E. Our E, and again, is going to be the 4.49. Let me write it in scientific notation. Liters per centimeter times mole, times the path length, which stays as 1 centimeter, times the concentration. Now keep in mind, this is the concentration of this sample right here. It's not the concentration of the lake water itself, which is the ultimate question. So let's go ahead and find the concentration of this sample, and then we can just figure it out from there, what it must have been in the lake. So if I take 0.385 divided by 4.49 times 10 to the third divided by 1, I get an answer of C equaling 8.57 times 10 to the negative 5 mole per liter. But again, this is in the 25.0 milliliter sample. Well, we only took 10 milliliters from the lake, so we want all of this came from this sample, and let me rephrase that, all of this came from the lake. So we have to figure out how much exactly was in the lake. It's got to be more concentrated than this because this is dilute. So let's figure out how many moles we had. 0.025, 0 times 8.57 times 10 to the negative 5 will tell us how many moles of ammonia were in there. This gives me an answer of 2.1425 times 10 to the negative 6 mole. And just remember that this was originally that many moles came from 0.0100 liters, or that 10 milliliters. So divided by 0.01 will give us an answer of 2.14 times 10 to the negative 4 mole per liter. And that would be how much ammonia was originally in the lake. So again, we just subtracted out the background. That told us our true absorbance here. And we had to set this equal to the molar absorptivity coefficient that we figured out by spiking the sample up here. All right, hope that helps.